Hi again, welcome to the first video about using geometric series to solve an annuity or superannuation investment problem. In this video we apply our technique for finding the sum of n terms of a geometric series. We do that after setting out the steps through which we develop the series. Subsequent videos for investments and also for loans extend the approach we outline here to questions asking related but different issues about investments and borrowing. A typical problem is the following. David wants to save for his retirement in a special account separate from his superannuation. He invests $150 at the beginning of each month in a special account, paying 6% per annum with interest payable monthly, and he intends to make these investments every month for the next 20 years. How much will David have in his account at the end of his plan? The first thing we need to do is to convert David's annual interest rate of 6%, which is compounding monthly, to a monthly figure. So we put it in the calculator, 6% divided by 12 months, which gives us 0.5% per month, or, writing it a different way, 0.005. Putting it in the calculator is like having a security blanket. You don't want to drop a zero at this stage, so just put it in so that you can see exactly what it is. Yeah, you can do some of them in your head, but others are pretty hard to do, so just do as a matter of course. So at the end of month 1, David has in his account the original deposit of $150 and the interest on that deposit that was paid at the end of the month, which is $150 times 0.5%. So writing that down more mathematically, we can say at the end of month 1, David has his original investment of $150 plus the 150 times 0.005 interest on the original investment. So we'll factorise out the $150 from these two terms, and we're left with 150 times bracket 1 plus 0.005, which we could write as 1.005, and for interest's sake that turns out to be $150.75. Now at the beginning of the second month, David makes another $150 deposit. So the investment at the end of the second month is going to be the value of his first deposit at the end of month 2, which is $150 times the 1.005, times the 1.005 again for the second month, which we can shorten to 150 times 1.005 squared, plus the value of his second deposit after 1 month, which is just like the first one, 150 times 1.005. So we add those two things together and we notice that there's a 1.005 in both, so we'll factorise out that term to give 150 times 1.005 plus 150 all times 1.005. So we're getting some sort of nice summary going on. So I'll take that summary that's coming up and just put it down in a form that we might be able to see better. So at the end of month 1 we have $150 times 1.005. At the end of month 2 we have 150 times 1.005 plus the 150 for the second deposit times the 1.005 interest at the end of the second month. Now for month 3 we have everything that we've just calculated for month 2 still there, so we just write that back down. And then we have another $150 at the beginning of month 3, and then all of that is multiplied by 1.005 for the end of month 3. So we can do some factorising here just to make it a little bit easier. Well, clearly the 1.005 at the end is outside the brackets anyway, so we'll write that down first. And we're then left with everything else that was in the brackets to start off with. So our second common factor that we can take out is the 150, because that appears 3 times in our expression. So we factorise out the 150 and we're just left with 3 terms. So I'll rewrite those down. So it's 1.005 squared by expanding the brackets, plus 1.005 plus 1, and then I'll, just for convenience, I'll write them back around the other way. So now clearly I've got a nice geometric series in my brackets. The first term is 1, the common ratio is 1.005, and I've got 3 terms. So I can use my sum of n terms formula to say that we've got 1.005 times 150, which was a bit outside, and then 1 minus 1.005 cubed over 1 minus 1.005. If some of you think that that's around the wrong way, then it's not. Have a look at the video on summing in terms of a geometric series. It's exactly the same formula. It's just more convenient. We can now generalise this for the end of 240 months, which is 20 years times 12 months. And that's going to be, the beginning's exactly the same, 1.005 times 150. And the only thing we need to change here is the 3 to 240. So it's the same formula to the 240th. And we put that in our calculator all at one time, not bit by bit, and we get $69,652.66. Now of this amount, David has paid $150 each month for 240 months, so he's actually paid $36,000 into the account. But nevertheless, his relatively small regular contribution over the time has accrued $33,652.66 for him. So well done, David. Now I have another friend called Daisy, and she wants to invest $2,000 into a superannuation fund at the beginning of each year. She's going to be paid 9% per annum interest on the funds invested, and that's going to be compounded annually. So the first part of our question is, how much did Daisy have invested at the end of the first year? Well, after 1 year, her investment was $2,000 times the interest rate, which is 1 plus 9%, which I've written as 1.09. So she's got now $2,180. The second part of this question is, how much was Daisy's first investment worth at the end of 25 years? Well, only one investment is being considered, so it's a straight compound interest problem. So after 20 years, the investment is going to be the principal, $2,000, times the interest rate, 1.09, raised to the 25 years. And that comes out to be $17,246.16. The third question is, how much did Daisy have in superannuation after 25 years? Well, we follow the same procedure as we did in the previous question. At the end of year 1, she had 2,000 times $1.09, which is 2,180. At the end of year 2, she had the 2,000 times 1.09 plus another $2,000, and all of that, in brackets, was multiplied by the 1.09. Now at the end of year 3, she's again got all of that amount plus another $2,000, and then everything gets 1.09 interest rate again. So I've written that down again so that we can start doing some factorising. So the 1.09 is already outside the bracket, so we'll put that down. And we're left with what you can see there. And now we've got a common factor of the $2,000 in each of the terms, so we'll now take that one out. And I'm just left with the balance of with the interest rates in there, which I'll rewrite by expanding my brackets, and I've got 1 plus 1.09 plus 1.09 squared. Again, I have a geometric series. It's got its first term of 1, common ratio of 1.09, and 3 terms. So I now need to generalise that. So if I'm looking at the end of 25 years, I'm going to have 25 terms. So I'll write my geometric sum down as 1.09 times 2,000, which were the numbers outside the geometric series. And then it's 1 minus 1.09 to the 25th over 1 minus 1.09. All of that goes into my calculator, at one time, not bit by bit, and my answer is $184,647.95. Well done to Daisy as well. An alternative approach to solving the problem stems from the first question that we asked about what was Daisy's initial investment worth at the end of 25 years. Well, the first deposit was, as we said before, $2,000 times 1.09 to the 25th. Now we move on to her second deposit, and that's 2,000 times 1.09 to the 24th. And the third deposit is the same to the 23rd, and so forth. So the 25th deposit, the last one, which she put in at the beginning of the year, so it's had 1 year of interest, is $2,000 times 1.09. So we add all of those terms up, and we have to factorise out the 2,000 and the 1.09. Here's our geometric series, and so we put that into the calculator and we get exactly the same answer. I'm not so keen on that approach because it's different to the one that we're going to use for loans, and also it doesn't allow variations as easily as the first method I showed you. So it's up to you, but I think I'd stick to the other one. In summary, the annuity questions you do need to be explained year by year to start with, for say 3 years. So you've got to set out your explanation fully but concisely. And as your explanation evolves, you search for a pattern that you can generalise. Once you've got that, you substitute into a formula for sum of n terms of a geometric series, and then you type in the whole formula into your calculator. Please don't try to do it bit by bit. It's a waste of time and error-inducing. Hope I have helped you to understand the necessary approach. Thanks for watching this video. In the next video in the series, we look at alternative questions within the same annuities area. Hit the like button and subscribe if you haven't already. That will give you an alert to new videos as they are uploaded. Then go and do some questions in Test Yourself 1 on my website at drjaysmath.com. Add a comment below if you have any questions. Good luck with your investing. See you later.